Codesignal, arcade, growing plant. Hello everyone, my name is Joshua and I'll be solving growing plant from the Codesignal problems. Let's begin. So I read this problem already. Let's summarize it. Each day, you're taking care of a plant. It grows up by upSpeed, a fixed integer, and it decreases by, at nighttime, downSpeed, which is also an integer. Now you grew this plant from height equals 0. And you want to find out, given the rate it goes from upSpeed to downspeed, when will it reach that desired height? The number of days it will reach that desired height. Now, this is an example. Like, for example, the upSpeed is 100, downspeed is 10, and desired height is 910. You can find out that if you look through how it traverses through this pattern of growing and decrease and shrinking, it eventually can reach, on that day, the height of 910 on day 10. And you can see that even though at nighttime it goes below that desired height, we still want it. What really matters is that it reaches that day where it reaches that desired height. Now, with that being said, we can think of some cases, like different cases, and they can help us create this sort of equation to solve this. Because I know that we could probably use a for loop or a while loop. I'm sorry, a while loop is a better way to say it. A while loop to find out when it can reach that desired height. But that could increase the time complexity. Is there a way to reduce the time complexity within constant time, and we can use constant space to solve this? So let's think about this. So let's take this one for example. 100 is upSpeed. Here, I'll do this. Up, downspeed, desired height. Let's make this a little bit more spacious. All right, 100, and it's going to be downspeed of 10. And desired height is 910. So in this case scenario, I guess we could calculate the rate it grows by up minus down, which in this case would be 90. Now, if we divide, thinking about this, like usually we could find the number of days by doing the desired height divided by the rate. In this case, it's going to be about like, okay, so it's going to take about 10 point something days to reach that desired height. But it doesn't account for that situation that it could reach that desired height right away within the 10th day, actually, because even though it goes down by a little bit, it can take a little while, we can still find out, it can still, since usually, we can't round up because 11 days is incorrect because it actually reaches the desired height on the 10th day. So how can we include that one? I would say that maybe the best way to look at it is to find the desired height. Let me see if I do this correctly. Desired height minus the upSpeed. In that case, all we have to do next, now we know that it's going to take 9 days with this consistent upgrowing and downgrowing, but we know that on the next day, it's guaranteed to be, it'll take one more day till it reaches that upSpeed of the desired height, which is, oh shoot, I subtracted incorrectly. Oh yeah, I did correctly, never mind. It's going to reach that height of 910 desired height. So whatever days that it'll take to solve this one, I could just plus 1 at the end of that one. Let's take another example. Can I look at some of the examples here? Let's see. 10, 9, 4. Let's just do this one. 10, 9, desired height is 4. This is a good example that on the first day it's going to reach that desired height because it's going to go up right away. So this is an interesting scenario because if I do desired height minus the upSpeed, it's going to be about -6 actually, which is strange. We can't really do much with -6, even though the rate it grows is by 1. That doesn't really incorporate anything because the upSpeed is bigger than the desired height. And there's no such thing as negatives too, negative days. What we can say is that it takes at least in the 0th day, take 0 days until, we just make it 0 days, because we know that it will take at least 1 day to reach the desired height. It can never be negative. We know that initially that this is a special case that there can't be any negative days in whatever you solve. So in that case, we just do 0 plus 1. So we know that at the very least, it has to be 0 days plus 1 day because it has to grow within that day. Let's see if we can find another example here. upSpeed 5 to 7. Let's try one more. 5 to 7. The desired height minus up, it's going to be 2. So the rate is going to be 2 divided by, the rate is going to be 3. desired the rate divided by desired height minus rate is going to be 2 divided by 3 would be like 0.666. But since it's going to reach the perfect height on the preceding day, we know we have to add at least 1. Now it's 1.666. Now we can have fractional answers. A day is considered a whole day. So what we can do is we have to round this up to at least 1. So I'm going to say round up to, let's just say 2 days total. And you can see that's why it is. Because, you know, there can't be a fraction of a day that reaches a certain height. It has to be within that same day. I mean, it's all days counted as just one whole value. So there's a few scenarios we have to consider. One, you can reach the desired height perfectly on a specific day, but even though it can decrease that height, we really want to find that day that reaches that desired height. So that's why we just calculate desired height minus upSpeed, and we can get that perfect number of days until, let me just add that 1. So we get that perfect number of days that it reaches the desired height when its last behavior is going up in that speed. And we have that situation where it could grow exactly on that first day. We can have that -6 scenario, so we know that at the minimum it takes 0 days. 0 days just to 0 days in between where it has that scenario where it goes up speed and down speed right away. It's just really just up height. And we also have the scenario that, you know, there could be fractions within that day, fractions within the number of days it takes to reach a desired height. But since, you know, we count whole days, we have to round up whatever days we calculate with that rate up to a perfect number, and then we could just add that 1 day since the up speed is going to reach it to that perfect height. So how do we represent this through a mathematical equation? So let's think about this. So we know definitely that it's going to take about, we have to incorporate that there's definitely going to be at least 0 days in between, plus 1 to reach that perfect height. So we know that again, the first day it could actually reach that perfect height because its upspeed would be equal or greater than the desired height. And we also have to consider, we have to round up if there's a fractional answer. A fractional answer to when we do this calculation to the rate, which is math.ceiling of a double of desired height minus upspeed divided by upspeed minus downspeed. And I think this should work. And the ceiling rounds it, but since we want this as an integer, it's right here. Let's see if we can extend this out perfectly. This is a much better way to look at it. So here's how it incorporates that. You can't have any negative answers, so we know that at least takes 0 days of going up and down to reach a certain height, where it's desired height minus upspeed. And since that, you know, we incorporate this upspeed when it reaches that perfect height as +1 right here, because on that day it exactly reaches that desired height, so we have to incorporate that one. Now we have to round up because we don't accept fractional answers for days. And if I run this test, I think it should be perfect. Okay, that's good. Whew, this was a dense problem, but I think we solved it correctly. Well, I hope this is helpful. If it's unclear, please describe it in the comments below. I'm going to try to make my answer as concise as possible. This is a peculiar type of question. Oh, sorry about that. And this is a peculiar question. I think, though, that through this answer you can understand how I solved it, and I'll try to make it concise as possible. Well, have a good day, guys. See ya.